Welcome to our second week lecture. In this week we are going to cover that basic assumptions for thin plate theories, von Karman non-linearity, development of governing equations, boundary conditions and then plate constitutive relations. Till date I have explained you that what is the virtual work displacement, what is the Hamilton principle and how to apply that. Now we will learn that for a specific case, how we are going to use the Hamilton principle to develop the plate solution, governing equations. So first the basic assumptions for a thin plate theory. As I have already told you, thin plate means when S length to thickness ratio is greater than or equal to 20, then plate is considered thin, like your thin beam, Euler-Bernoulli beam. So, Euler-Bernoulli beam is assumption for one dimensional case. So, Kirchhoff's first time I would like to say extended the one dimensional assumption to the two dimensional assumptions. And what are those assumptions? Like first, straight line perpendicular to the mid surface before deformation remains straight after deformations. If this is my straight line perpendicular to the middle surface, so this line remains straight before and after deformations, and the transverse normals do not experience any elongations, means there is no stretching along the thickness direction. It means the strain along the thickness direction is considered negligible. And the last, the transverse normal rotates in such a way that they remain perpendicular to the middle surface after the deformations. So, mathematically I am saying that there is no rotation, no shear rotations, basically transverse rotations. So, shear strain, which is a measure of the rotation basically. When you talk about a normal strain, which is the measure of the elongation or a stretching, whereas shear strain is a measure of deformation in angular positions, the angle, rotation. So, there is no shear strain or we are neglecting. The concept or physics behind this assumption is that since plate is thin along the thickness direction, so and it is subjected to the small deformation case, means the deformation or the deflection is very small, so it will not cause any shear strain or any stretching, thickness stretching in the body. So, these are the basic assumptions. If you would like to compare with the Euler-Bernoulli beam, then there you have epsilon zz and gamma zx is 0. When you are talking about a plate, so gamma yz is also 0. So, that Kirchhoff's extended the one dimensional hypothesis to the two dimensional case. So, this is my x axis, this is my y axis, this is my z axis, and the center of that will be the mid plane. There are number of ways to assume the displacement field, that how to assume a displacement field. The very first way, using the mathematics, as in the hypothesis it is said that epsilon zz is 0, normal strain along the transverse direction is 0. So, if we put it is equal to 0 and integrate this equation with respect to z, Since this is a partial derivative along z and we have a function x, y, if we talk about the special functions and z. So, the constant, integrating constant, it will not just a constant, it will have a function in x and y. So, at the middle plane or reference plane, when z is 0, w is w naught. So, basically coordinate of z is taken as central and minus h by 2 and plus h by 2. So, when z is 0, w is equal to w naught, u equal to u naught and v equal to v naught. Generally this is the assumption. So, if you put f integrating constant is nothing but w naught and which is a function of x y, because at the mid plane only x and y, z equal to 0. So, therefore, we can write w, or you can say also time if you want to take. So, w in journal is a function of x, y, z and t and it equal to w naught, a constant along the thickness. It means if you want to plot, if this is my thickness minus h by 2 to capital H by 2 and you want to plot a w, what will be that? Just a constant line. Let us say my w is coming something 7, if I say the non-dimensionalizing mode, just 7 of that. So, it will just a straight line like that, any number. So, along the thickness is a constant, not a function of z at all. So, 90% theories we consider w is just w naught. But when we talk about a refined theories, or if we are interested to accurately model the behavior of a thick plate, then or even these days we can consider some more functions z times of w1 plus z cube of w2 later on. So, but that is the feature of a more refined theories. So, in the latest paper in the literature you may find that w is just not w naught, w may be w naught plus z times of w1 plus z cube of w2 etc. Now, the second assumption that shear strain is also negligible. So, definition of shear strain is del u by del z plus del w by del x equal to 0. So, from there you write that del u by del z is nothing but minus of del w by del x. If you integrate the equation to both sides, so z times of w comma x and f2 integrating constants. Again at the middle surface putting z is equal to 0. So, this term will vanish, u is equal to u naught. So, f2 will come u naught. So, we can directly write that u can be written as u naught minus z times of w naught comma x. So, this tells you the variation of u along the thickness. So, what is the variation of u? Linear variation, like if this is minus h by 2 plus h by 2, it will be very linearly like this or like this. It depends upon that value, whether it will be at the bottom it will be negative or positive, it depends on that. So, linearly varying across the thickness. Similarly, gamma yz definition, and if you equate to 0 and integrate with respect to z and putting the middle surface at 0, v is equal to v naught. So, we can be find it out v naught minus z time w comma y. So, you see here based on the assumptions we can find out the variations of displacement variable across the thickness. So, finally, we have this assumed displacement field, what you call, sometimes you may say assumed, sometimes you may mathematically derive, but this mathematical derivation is only possible for classical plate or cell case. If you are interested for a first order, third order, then those kind of things cannot be done. There you have to assume a series. So, but for a classical, or I would like to say Kirchhoff's plate, you can also derive the mathematically, that u is nothing but u naught z times w comma x, v is equal to v naught minus z times w comma y, where w comma x, w comma y is nothing but the partial derivative of w with respect to x and y, and w is equal to w naught. I think in the first week lecture I have already explained, if you are interested first order theory or third order theory, so what will be the assumptions, that this u will be u naught plus z times phi 1, where phi is unknown rotation. Here rotation is this much, known rotation in terms of w. V will be v naught plus z times of, you may say, psi 1, w is w naught. So, this will be the first order shear deformation theory. In the assumptions that we say in first order, epsilon z is 0, but gamma yz, gamma zx not equal to 0, that shear strains are not 0. So, if you do not follow, if you have this kind of conditions, then this will be unknown rotations. Similarly, in third order, you have some third order terms. There also that epsilon zz is 0, but gamma yz not equal to 0, gamma zx not equal to 0. Here I would like to tell you the limitation of FSDT, that whatever shear stress you will get, they are not very accurate. So, we use the shear factor, shear correction factors. So, that is why people prefer, in case of FSDT, third order theory, here no shear corrections factor are required. Further, it contains a cubic variation. So, it may accurately predict the behavior of thick plates. Then what is our next step? The next step is to choose a suitable strain displacement relations. This is also a very important step, that you have to choose as per your requirement, whether you are going to consider the non-linear part or linear part, non-linear part or not, or some component or not, or you want to take fully. So, I would like to just write the full expression of a W epsilon xx, that it will be del u by del x plus half del u by del x whole square plus del v by del y whole square plus del w by del x whole square. So, this corresponding to the linear and this corresponding to the non-linear contribution. So, if I have said that von Karman non-linearity, or sometimes we called geometric non-linearity. So, here you are seeing that in epsilon xx, I have considered a term u comma x and half of del w by del x whole square. What is that corresponding? Why I have considered only this? Why not this? These two. The assumption behind that, since plate is thin and we have applied only transverse loading, so we will say that this deflection is more comparison to u and v, and their derivatives, since u is small, so their derivative will also small, and further square of derivative is also small, negligible to 0, or I will say small. Compare that del u is small, so their derivatives will also small compared to w. And another thing, that rotations, we say that moderate rotation, there we assume that there is a slight rotation we assume, that is why this term has been considered. If you see in the basic relation, we are also that w comma x, that belongs to a rotation. So, a small term which is equivalent to w comma x rotation, that is exists. So, we take care of this. So, if you assume, so here in epsilon xx you have 1, 2, 3, 4 terms, out of that we have chosen 2 terms. Maybe later on or these days you may choose all. If you have a plate is thick, deformation is large, rotation is large, then you have to consider all the terms. So, you have to, as per your requirement, you have to choose or you have to consider. So, initially that von Karman considered this, because in olden days there was no very big computing facilities. So, even solving with this kind of term, taking a single term is a huge task. So, solving a simultaneous set of ordinary equations or doing some further calculations. So, I am also giving a first course in this area. So, I am just limiting myself considering only this term. So, if we consider del w by del x or del w by del y or the mixed derivative, then it is known as von Karman non-linearity. Or geometric non-linearity. Why we call, or sometimes kinematic, because they are taken in terms of kinematic relations, that strain, all this. So, this was the major step, that what strain displacement you are going to follow. If you are going to follow a linear or a non-linear or a partial like us. Now, in the third step, you have to obtain the, I would like to say, drive or rewrite, whatever you want to say, strain displacement using the displacement field. What is that displacement field? This is our displacement field. If we have u, v, w like this, so what will be my strain? Epsilon xx. So, del u naught by del x, del w comma double derivative del x and this term. Now, you can arrange, this is first derivative, this is first derivative. So, we are putting it together and this is double derivative. So, basically these terms are putting together are denoted as epsilon xx naught, and sometimes we called it is a membrane strain or middle surface strain. Then double derivative term is denoted as epsilon xx1. So, we called it as a bending strain or a flexural strain. Contribution and stretching strain. Similarly, the components in epsilon yy. So, epsilon yy will be del v by del y. So, from there double derivative along y, del y and non-linear component. We have to rearrange epsilon yy naught, epsilon yy1 and gamma xy. Gamma xy is del u by del y plus del v by del x. So, if you substitute those things and arrange those terms, first order terms, so you will see this is gamma xy naught, sorry this one, and this one is gamma xy1. So, why we are arranging like this epsilon xx, epsilon yy, gamma xy? We can proceed even without rearranging also, but for programming point of view, for further development point of view, if we can arrange these terms in a shorter form, we can recall, we can remember the things easily, and programming also. So, in the programming you have to just like a column vector epsilon xx, epsilon yy, gamma xy, and first will be epsilon xx naught, epsilon yy naught, gamma xy naught plus z times epsilon xx1, epsilon yy1, gamma xy1. If you already based on these assumptions, we have developed this. Again you can verify also. If you substitute these things, so our three strain components will be 0, epsilon zz, gamma yz and gamma zx. So, we have only 3 non-zero strain components. Since we are going to use a Hamilton principle, we may need a variation or I would like to say that first variation in the displacement or first variation in the strains, those terms we require at some stage. So, I am going to find out if this is my displacement field, what will be the del u? Del u will be nothing, del u naught minus z times of del w comma x. Similarly, what is my virtual displacement or the first variation along y direction in displacement? Del v naught minus del z, del w comma y. Similarly, del w naught. Now, del epsilon xx will be del epsilon xx naught plus del epsilon xx of 1. Very easy to remember. Then in particular or explicitly, del x naught is nothing but del u naught comma x. So, from there to get cancel out, first function as it is del u naught by comma x and del w naught comma x. So, finally you can write del u naught comma x plus w naught comma x del w naught comma x, first variation of this. Similarly, what is del epsilon xx1 minus? So, first variation is nothing but it acts as a differential operator. One can go through internet or Google or a book of J. N. Reddy, theory of potential there or theory of elasticity. It is clearly explained that it acts as a differential operator and its rules also same. If you divide or multiply or add, follow those rules. Similarly, del epsilon y naught, del v naught, w naught comma y and del w naught comma y. Similarly, del epsilon y of 1 and gamma xy of 1. Sometimes it looks very easy when it is on the presentation or on the board, but when I give you actually to solve or to find out the variation, it may be difficult. Sometimes people may get confused. You see here Z kind of thing. Most of the time when I used to take a class of theory of plate and shell, students used to ask, you want to take del u of this is fine, but it remains same Z. You have taken only variation in this, why not in the Z? Or sometimes it may be x. So, known quantity like your references, coordinate system x, y, z, you know coordinates at particular point, that what will be my z coordinate, what is my x coordinates, there is no ambiguity. So, no variation. When you do not know and you want to extrapolate something, okay, what will be the my value, so then you have to take. So, the coordinates which are known or the values which are fixed, which is not changing, means at a point x coordinate is known to you. So, if these things come, do not take variation. Sometimes my students do that, del u naught minus del z, w naught comma x blah blah. So, this is the wrong. So, coordinates, in the coordinates there will be no variation, or maybe some just you will put 2 constant, it remains as it is. When you go for a differentiation, let us say y is equal to x plus 2 or x square plus 2. So, if you take differentiation, it will be twice of x plus 0 instead of this. But if you say that del y, it will be x del x plus 2, simple, you need not to change it. Or sometimes in the multiplication 2y, you just put 2y as it is. So, when you are taking the variation, you have to be careful. So, maybe for a higher order theories, maybe some more terms z cube, z square, z 4 times, they will remain the same, there will be no variation in that. So, I think this point is clear. We can move now. Our fourth step, framing up the principle, which basic principle we are going to use. If we are interested only in the static analysis, then go for principle of virtual displacement. If we are interested to find out the dynamic behavior of that plate, then Hamilton principle. So, I have also would like to say that you see that T here, time, that u is also a function of time, that 3 spatial coordinates and 1 time coordinates. That is why I am going to use a Hamilton principle. So, in the Hamilton principle, kinetic energy minus, okay, it is written wrongly, Wi, it should be potential or whatever, say work done. So, if you substitute like this, so del Wi plus del Wi, external work done minus internal work done, kinetic energy, dt tends to be 0. So, first variation in kinetic energy, first variation in internal work done, first variation in external work done. Explicitly or in index form, what is that kinetic energy? First variation, that rho ui dot del ui dot. What is that? Internal work done, sigma ij del epsilon ij. What is that? External work done, Ti and del ui over that surface and dt equal to 0. So, actually if you talk about a discrete body, your kinetic energy is nothing but half of mv square. I have also again discussed these things. So, for a continuous system, if mass is distributed over a volume, then instead of this we will put R remains same, rho into dV over that volume, that will become a mass, and u is a displacement and u dot. So, when you have a spatial differentiation, then we will put the comma, that u comma x. When we have a time derivative, then we will put a dot over that quantity. It means del u by del t equal to u dot. So, this is the standard notation followed in the textbook of plate and shell, that u dot means upper dot, that variation differentiation with respect to time. If you say u comma x, it means del u by del x. So, our kinetic energy is this. If you take the first variation, then you say that twice will come up here and ui and del ui dot. So, basically first variation and kinetic energy becomes like this in index form, where I can go 1, 2, 3. So, for our present case, del k can be written like this, u dot del u dot, v dot del v dot, w dot del w dot. Further, what is u dot? U dot is u naught dot minus z time w naught comma x dot. Similarly, their variation, del u dot minus z time del w dot comma x, v naught dot minus z time w comma y, and del v naught minus z time w naught comma that, and here only one term w naught and del w naught into dv. So, this we have for our present case. Suppose if you have a third order theory, maybe some more terms required. If you have some other theory, maybe some different kind of combinations may be there, but the process remains the same, that whatever you have assumption you have to put it here. Now, next you multiply, open the brackets, first you multiply this to this. So, u naught into del u naught, first contribution. Then I have already arranged in such a fashion that constant and z times and z square, then again v naught del v naught second term and del w naught this third term. So, 3 contribution. Then the function of z. So, minus z del u naught w naught comma x, this one. Then minus z del v naught comma again this and this, sorry, u naught del w naught comma x. So, from there 2 contributions, one from this and one from this. Then one from this, one from this, z contribution. Then z square, z and z. So, it will be plus only one contribution and one contribution. So, now you have a 3 terms inside that constant case, 3 terms 1, 2, 3, 4 terms inside that z and 2 terms the coefficient of z square. So, we are on the volume integration. Now, the concept of moment resultant comes into the picture. Basically, any 2-dimensional theory, this is the very important step, that how to reduce 3D to 2D. Or I will say the 3D case. Now, it is on volume, if we say the moment resultant, mass moment of inertia, then it will be, so the definition of mass moment of inertia here is minus h by 2 to plus h by 2 rho times dz. We say that, let us say it is equal to a some constant which is denoted by I naught and equivalent to the mass moment of inertia, okay, equivalent to that. Then you define I1 minus h by 2 plus h by 2 rho times z dz. Similarly, you define I2 rho z square dz. So, for a symmetric case, when you are talking about a single layer and symmetric plate, that then this, if you do the integration, what will be that? Z square by 2 and rho times, and you put the limits, it becomes to 0. So, generally I1 will be 0. So, the final contribution in the kinetic energy terms, the 3 I naught and 2 I2 contributions. So, here I would like to proceed it further in the kinetic energy. In actual, you can write equal to 0. ठीक है. So, we are going to evaluate now this one. Del k, now we know what are the terms in the del k, and you put time integration over there and put the terms dA dt. The concept further evaluation is this, because we know our primary variables are variations del u naught, del v naught, del w naught. Other than this, if there is a derivative, time derivative or the space derivative, we have to get rid of that, because we have no information about that. So, we have here del u dot. So, this is not going to be there in the main set of equations. So, we have to get rid of that. You know only the information, or you have taken the arbitrary variations in u naught, v naught and w naught, not in their time derivative. So, their time derivative must not be there, or we have to get rid of their time derivative. If there is also space derivative, there also we have to get rid of that space derivative. So, but here we see in kinetic energy time derivative. So, like as I explained in the first week of lecture, for the case of beam, you can write like this: u naught, del u naught and time derivative. So, what is the rule? That differentiation, or you can say that second function as it is, differentiation of first function, plus first function as it is, differentiation of second function. So, from here you see that del u naught is nothing but u naught del u naught time derivative minus of del w naught del u naught. So, I will explain only for one term and similarly apply for other terms. So, I have taken this one term. So, this term can be replaced with this. Now, this will remain on area, and it is fine with us that del u naught variations in primary variable, naughts in its derivative space or time. Then again this derivative with respect to time and time integration is there. So, it will be integrated over time and putting the limit over there. Now that from time dependent problems, admissible virtual displacement must also vanish at the initial time and final time. If you have a function and you have a variation, so if this is my initial time and this is my final time, so it is exactly matching with, there is no variation, that should be vanished. So, del u naught, only in between is del u naught, but here is equal to 0. So, this will vanish, so this term will not contribute at all. So, you see from this term you have a contribution of u naught double dot del u naught dA by dt. So, there they have written slightly dot over there. Similarly, this contribution will be, one can tell v double dot and del u naught, from here double dot del w naught contribution, and from here also. So, finally, we can write this contribution and this thing dA by dt. So, you can put it some outside bracket. So, this is very important step, that obtaining a contribution of kinetic energy terms. So, for a particular case of theory, whenever you are going for a advanced material, there may be some more terms or some other contributions, may be mechanical, other than some, maybe some more contribution may come. So, this you have to drive properly. If one is interested to develop a program or develop a solution for any plate or any structure, very first requirement is that theoretically or the mathematically formulations should be absolutely correct. There should be no mistake, no errors with sign, all these things. So, you have to check whether my signs are accurate, whether these assumptions are accurate or integrations, everything you must verify at this step. So, first you find out for a particular structure, for a particular advanced material structure, that what are the contributions or the terms inside my kinetic energy regime. Next, now we are going to obtain the contribution due to the strain energy, or I would like to say that internal work done, first variation in the internal work done. Since 3 strains are 0, so their variation will also be 0. So, only contribution in internal work done will be from sigma xx del epsilon xx, sigma yy del epsilon yy, tau xy, gamma xy and volume integration. Suppose you are going for some different theory, maybe some more terms may be there, which may be corresponding, contributing to the internal energy of the body. Some may be magnetic terms, some may be piezo terms, if we talk about advanced materials. Some may be piezo contribution, magnetic contributions. So, if you have understood this concept, and if you are interested to, and if you read any research article in which a piezo or a magnetic kind of thing is done, you can directly understand, okay, this is your mechanic contribution in the strain internal work done due to the mechanical plus due to piezo plus magnetic, corresponding part of that. So, I think with this introduction one can develop for a different kind of material, for a different kind of geometry. Now, what is epsilon xx? Del epsilon xx is nothing but del epsilon of xx naught and plus z time del epsilon of xx1. Similarly, epsilon yy and gamma yy. Now, again The very important step, it is the integration over the volume. How to convert it to two-dimensional case, x and y. So, we define the stress resultants. So, basically nxx minus h by 2 plus h by 2 sigma xx and dz, sigma yy and dz and yy, nxy minus h by 2 plus h by 2 tau xy by dz. These are known as in-plane stress resultant nxx, nyy, nxy. Similarly, you see that z terms is here. So, z time of sigma xx क्या होगा? Moment mxx, myy, z times of sigma yy. Here z times they have didn't put actually. Then mxy, z times of tau xy dz. So, using those stress resultants, we can rewrite del wi time to nahi like this. Clear? Now substituting explicit strain values, epsilon xx naught. Now you may recall that, what is that? Del u naught comma x, w naught comma x, del w comma naught. Similarly, nyy, then nxy, then epsilon xx 1, epsilon yy 1 and del w comma xy, gamma xy 1. Now you see nxx del u naught comma x. I have already put a stress that we know only del u naught. This is our first variation or our primary variable. This is not. We do not have any information about their derivatives. So, we have to get rid of this. So, the basic step you put derivative. So, nxx comma x del u naught comma and nxx del u comma x. So, basically this term can be written as nxx del u naught whole ka derivative comma x minus nxx comma x del u naught. So, this term, this term, this term, you can proceed in a same way. Similarly, you have a contribution due to this. Here again you have to put it nxx w comma x as a one term and then you have to proceed. So, you can write nxx w comma x del w comma x nothing but equal to nxx w comma x whole ka derivative comma x and del w naught minus nxx w naught comma x comma and del w naught. Then you have a double derivative here. So, from this you have a two terms contribution. So, this one term will give you these two terms. Now, mxx del w naught comma xx, how many terms it will give? You see, first you take this term mxx comma x, mxx del w comma x. So, this can be written as like this. This is okay, but this is not okay. Again you have to split it up and finally, this term gives 3 terms. So, basically 3, 3, 3 and here 2, 2, 2 like this you have number of terms. So, finally, you see 1, 2, 3, 4, 6, 7, 8, 9, then 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 and 25. So, now we have 25 terms. Out of these 25 terms, some of will go to the area integral and some of them will go to the boundary integral. So, it is very much important if you are developing a theory. So, at this stage you mark all these things, how many terms, and you have to rearrange those terms, some terms under the area and some terms under the boundary. You see this whole term derivative comma x will go to the boundary, the underlined terms will go to the boundaries, and this and this and this and this and this and this, again this and this will go to the boundary, and the rest of the terms, second number terms, will be on the area. So, I am going to see that area nxx nyy and clubbing its similar kind of coefficients of del u naught, coefficients of del v naught and coefficients of del w naught putting together and some boundary terms. So, in the next lecture I will explain the rest of the boundary terms and we will proceed further.